So I will start with some review that we have. Actually, most of you know error corrections already. You took QS last semester. But let me just review this idea. We start with classical bit channel. Okay, so you have, let's say, for example, we use 3, 0, and 3, 1 to represent logical 0 and 1. Okay? And assume this kind of bit channel. So for example, 0 has some chance to flip to 1 with probability P, and 1 has some probability also the same P flip to 0. We define the kind of symmetric bit flip channel. You can also consider non-symmetric, but this is probably the easiest to illustrate. Okay, so if you look at this, consider the probability. So 0 will stay 0 with probability 1 minus P to the cube, but it will flip to 0, 0, 1, 0, 1, 0. See, how do I use it? Yeah, so this would have probability, okay, each with 1 minus P squared of staying, right? And then P is the flip, okay? So, and these two groups, they are closer to the original, right? In terms of Hemingway, this is same, and this is Hemingway 1. And here you have Hemingway 2 that appear with probability 1 minus P squared times P. Sorry, 1 minus P is staying, and then P squared is flip. So there are two ones. And you could also flip to a 1 with probability P cubed. And these two green ones have Hemingway larger than 1. Okay. So in terms of the correction, we can use the majority vote, right? And we can correct the first, the second group here as error. Similarly, 111 as logical 1 can stay with 111 with probability 1 minus P to the cube because this is probability of staying. Or converted to 110, 101, 0, with each and has probability 1 minus P squared times P. And these two can be corrected. They're correctable. The remaining two are not correctable because if you use majority vote, you would think this is a 0, logical 0, and that's not correct. So the error after this one, this encoding only occur at the later groups, right? So you just add these two, PQ plus 3 cases, 3 times 1 minus P times P squared is the error after you do this encoding. And you can plot this curve. This is P prime as function of P. And this is a straight line. P prime equal to P. They cross at actually 0.5. So that means if your initial error is lower than 0.5, after correction, it will lower. After the encoding, the error rate will lower. If the initial error rate is bigger than 0.5, it would blow up. It will amplify the error. And then we saw that therefore, if the error rate is sufficiently small, we get some advantage of doing encoding. So this is the classical bit channel, and the redundant encoding help. Right, this redundant encoding, in the quantum case, we could also do something similar. We use 3, 0 as a basis, 0, logical 0, and 3, 1, 3 physical qubit as logical 1. However, with the mention, we cannot encode. We are not trying to encode uh this kind of state, right? We are not encode this. Right? We're not trying to like read three identical copy for quantum state. Because this is not generally possible due to no cloning. Okay, so the best we can do is at least do these kind of encoding for the bases 0 and 1. Okay, and this is really showing a circuit is a circuit to create a GZ state, GZ-like state. This is for now. It's really a simple circuit. We have seen more complicated circuits, and in order to correct, right, you have to see the majority vote. You know, you need to know what the how many get flipped. Okay, so but you don't want to directly measure each qubit because that would collapse the wave function. Let's say if you measure 0, 1 in this qubit, then we collapse to either A00 or B times 111. So instead, you want to actually compare the difference. So you compare the difference, bit 1 and 2. You can measure Z1 and Z2. If they are the same, the Z1 and Z2 will give 1. Okay, if they have different bit flip, like 0, 1, 1, 0, then Z1, Z2 will give a negative sign. So you can know which pair has an error, and then also measuring the other pair, then you can uniquely identify which should be being flipped. So for example, this could be 0, 1, 0 plus B 1, 0, 1, and you compare there is a minus sign, there's minus sign, minus sign, and minus sign. So you can infer that bit 2 was flipped. Okay, so this is a really simple example. Then you can also ask, how do I measure this in terms of circuit? So this we would use the ancilla. So this 1, 2, 3 is already encoded qubit. So this will be of this form, or up to flip, up to X, for example, if we consider the bit flip error. And this allows us to measure the ZZ. Some sense is in a superposition, creating this in a superposition of psi, and then 1 with ZZ identity, I think psi. If you do the measurement, this basically is doing this. And if you have an error, so example, you have an error, then you have a minus sign, right? So this minus sign combined would take this initial plus state to a minus state. So if you then you do the Hadamard and Z-based arrangement, you can see that. So this is actually a phase kickback. This uses phase kickback we talked about earlier, actually in Deutsch algorithm. Okay. Yeah. But in quantum mechanics, you don't necessarily has error in bit flip. You could also have phase flip. In that case, it could be the simplest would be the Z error, for example, Z error. Z error flip plus to minus because it's a relative phase, and minus flip back to plus. You can also correct them if you are in the dual basis, the plus minus basis. If your encoding is that. So if we have a logical 0 encoded in 3 plus, logical 1 encoded in 3 minus, then a phase flip in the Z basis corresponding to a bit flip in the X basis. So this is equivalent just by a transformation Hadamard that you can deal with this error. Okay. But these are two different codes, right? This is Z basis, this is X basis code. So in the classical code, you don't have these kind of things. You don't have a different basis. But we cannot realize it simultaneously using just three qubit. So we cannot correct phase error if we use this encoding. If we cannot correct bit flip error if we use the X basis encoding. And actually one of the earliest quantum error correction code that can deal with any single qubit error is Shor's 9-qubit code, right? So we talked about this last semester, but just to review, I think the genius of Peter Shor is just to say that, okay, we cannot encode both error correction code in 3, so let's expand that into 9 qubit. So what he does is, okay, this plus state is 0 plus 1, 0 plus 1. So why don't we expand that? This is X basis, but they expand into the Z basis, but I just do the encoding to become a 9-qubit encoding code. Right? So yeah, so I don't have any further slide for the shows error correction code, but this is how you encode. You do GZ creation into the plus state, you create these plus 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 superposed with minus minus, and then you do another layer here with GZ creation. So basically copy this. And you can verify that they can correct the Z error. Sorry, let's just consider X flip error, bit flip. So bit flip in the first group of the 3 qubit can be detected by the previous bit encoding, redundant encoding. So any of the, and also the second group, third group, they all being considered in the same way as previous. So we only consider, for example, just 1 qubit error. So you could also have Z error. Z error, it could happen on first qubit, second, third, right? But actually the effect is the same. Any of the phase flip error on any of the 3 would create a minus sign. But this minus sign can be detected by something similar to here. You measure actually you measure the Z XX. So if you measure XX, you measure XXX, XXX. So XXX is somehow a logical encoding of X because it flipped the 0, 3, 0 plus 3, 1 to each other, and therefore if you have a minus sign here, it would generate a minus sign. So then you measure that phase difference, and this allow you to identify which group has Z error, and then you can apply the Z correction to any of the three qubit of the identified group. Yeah. So this code is called degenerate because the syndrome doesn't uniquely identify where the error, and actually doesn't matter. So in your homework, you did the redundant encoding, uh, not the short error correction code. Maybe I could have another homework on this. Let's see. Maybe we can briefly take a look of our homework. Okay, let me share this other screen. So you did this lab. Yeah, this code is modified, so it should work for the current Qiskit version. 3-qubit code. This is assuming the encoded state is psi, and then you will encode into 30 plus I times 1. And this is just to ask you to create a state. And this is the circuit we have, right? GSE circuit. First, you need to create this and you do the GSE. So 2C now. Okay, this is just plotting that. So implement the parity check, okay, to detect the load and localize the single bit. So here is just a function that has applying to apply the bit flip. Okay, so this is which qubit that you would apply, and this is generated randomly. So we apply to your qubit, then you will need to figure out which qubit it was flipped. Okay, so this is just to do that, and you already worked out the detail of this. So the syndrome is what I have in the slide. The syndrome is I have here, right, here to check the ZZ. Okay. So you already played with this and you can figure out, and then you apply the X to correct. Uh, yeah. So yeah, this is logical X, as I said, product of three X flip 30 to 3 1. So this is a logical gate. Okay, so this is the dual basis code in the plus 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 and minus minus basis. So basically, and it's similar. So this would apply the error of a Z, and then you would construct the syndrome measurement, and find which qubit has which it doesn't it actually yeah it would tell you which qubit was flipped, and then you apply the corresponding z for flip back. Yeah, we also know that this is a stabilizer code. That's actually where the syndrome is. Let me just quickly go over that. Mhm. Okay, so the stabilizer, this is a stabilizer code. So the stabilizer operators are Z1, Z2. Oh, it's already here. Okay, but Z1, Z2, Z2, Z3, Z3, Z1. Okay, of course, it include identity, and they form a group. Okay, so with the stabilizer, you can check that yeah they satisfy these s equal to psi, adjunct psi equal to psi. Okay. And there are only two independent one. For example, you take Z1, Z2, and Z2, Z3. It's only 3 qubit. You have two constraints, so that means there's one logical qubit left for you to encode. Okay. Yeah. Uh, now you have worked through this stabilizer construct. Here is a phase estimation circuit. We talked about phase estimation last semester. Um, we may come back with coding later, but this is the simplest coding here. Yeah, so there's one homework. This may not be a required part. Let's see. Yeah, you already finished it, and if you had work on this, you can practice the stabilizer code, or you had practice. Yeah, I will post the solution later. Any questions on the theory on error corrections and the even the notebook here? You already submitted the homework 2 weeks ago or 1 week ago. 2 weeks. Okay. So at least you have a good understanding of the basic error corrections. However, the current machine are noisy, and there are not many examples. There were a few examples that if you do the encoding, you can actually achieve better than without encoding. But for many current machines, the error rate is still too high. For example, you can take a look. Let me see if I can go to that website. If you look at, for example, these devices from IBM, the error rate, for example, 2 qubit error rate for this is probably the best machine among all these. The best is 10 to the minus 3. Layered, their error rate that would be introduced in this lab 3, I think, or lab 2. And you can see this the best 2 qubit error rate 2 times 10 to the minus 3. Older machine has higher rate. Yeah. So you click. There are also other error, not just the gate, right? We know the gates have errors. There's also the readout, as you see here, readout assignment. Right? What does that mean? It means when you when you're trying to read 0 and 1 as output, the 0 may actually be 1, 1 could actually be 0, and it's very similar to bit flip. You can think, you can also, if it's a classical error, you could regard it as perfect outcome with a classical bit flip. Okay, so you also have to deal with that. There's one thing that they did not list here. Okay, they also list these decoherence rate, relaxation, and decoherence, T1 and T2. So for example, the T1, this machine, T1, the maximum is 400. I think maybe the unit would be microsecond or nanos. Yeah, I need, oh yes, microsecond. So microsecond, that this maximum decoherence time is 400 microseconds, which is close to milliseconds, quite large. So the larger the decoherent relaxation time, the better the machine. This is T1, this is a T2. So you can look at this. And there's also other error, CZ errors, right? Readout error. There's one error that they did not list, which I think they should have internal characterization of that, is the state preparation, right? If you prepare 0, do you believe that it's actually 0? Yeah, so these kind of error was not listed, but I think internally they would have something. Okay. So leads me to the discussion on error mitigation. Let me switch to the slide. So this is based on some discussion in particular this paper by IBM's group. Mostly this is for discussing the gate error. The basic idea is that you want to implement some gate. It was produced by some pulse in their machines, maybe microwave pulse or something else, like gate voltage or something. So I can just plot with this, and generally the area representing how much you want to rotate. So you would have different possible curve. Ideally, they should achieve the same action, a different spread of the pulse experience different errors. So they can actually have the same actions, but with different error strengths. So the idea is to assume that this is a small error, so you can do data expansion. So you can do data expansion. This lambda representing the strength of the error. And lambda goes to 0, that would be the ideal. 0 error expectation value. Okay. So there is some trick that I use Richardson extrapolation. But you need to you need to know a few different strengths in order to do the extrapolation. Right? So you can see They just implement a few different house. The more you know, the more the the more accurate you can get because you can uh, eliminate more lower order errors. Okay. Yeah. So basically that's the idea. And so you could in the experiment you could see that they usually make view plot like that. This will be strains, let's say maybe the strains gamma one, gamma two. Okay, let me use lambda. Okay. We can do something else. Let's say this is lambda. One, the two, the three, and this is observable. And maybe you have a few points like that. And so what you do is you sort of extrapolate this to the zero lambda, and then say this is your expected noiseless result. Of course, do the extrapolation can increase the standard deviation. Yeah. So another error that I talk about. So I have okay. This is says you start with circuit, say preparation, and then you do some gate. We just talk about gate, right? There's also measurement or readout. They can also have error. Yeah, so we did some work this previously. The measurement is not entirely classical, the measurement error. So the measurement error, so ideal measurement is implemented by the projectors. Now, I already finished writing and it just appeared like it's the problem I'm using. So this is ideal measurement, right? Uh, realistic, you would write this will be M0 and M1. They are non negative operator. So in the ideal case, P0 would be trace this by a state, a density matrix, P0. P1 would be oh, somehow yeah, okay, this is correct. P1 would be this, okay. But realistically, this would not be the case like that. So this will be an operator, and they have to add up to one. And P0, P1 will be trace M0 and 1. And this is your density matrix, your state. So you can what you can do is you can assuming here we need to make some few assumptions. To do that, you would to calculate the readout, you would assume the gate is low error, and of course the state provision is good. And then in order to do that, you can say I want to prepare 0 and see if it's 0 or 1. I can also prepare plus state, minus state, or plus minus I. I can feed the machines uh these different by doing the preparation, including the gate, and you can measure 0 and 1. This is usually called detector tomography. And there's some trick. So these M's, you can generally write M is, let's say, alpha 0 identity and alpha vector dot poly. Right? You can always decompose a 2 by 2 permission matrix into this form. And this allow you to characterize this A0 and sorry, alpha 0 and alpha vector 1, 2, 3, or XYZ. The one that's classical is alpha Z is classical. Okay. And there's a way to ensure that you can filter out the error to be classical. Is you insert a Z gate before you do measurement, or no Z gate. So randomly, because you sort of randomly averaging the Z, and you know Z anti-commute was X and Y. So sigma X and sigma Y will be averaged out. Yeah, I'm giving more detail than this. This is a way, so randomly add Z gate before measurement. Okay. It's still, oh, it's meant screw up my writing. Before measurement. You can actually, this would make readout error classical. Bit flip. Okay. And we have actually done some characterization. I'm not showing in the slide, but um, mostly the error comes from the Z direction, alpha Z. And alpha X and alpha Y are small. So, okay, so this is a long introduction to this slide. Assuming it's now classical, what you do is you just prepare N0 and 1 are these 0, 1 bit string. You prepare these and then measure them separately. Okay, 0, 1, and see what's the output. For example, this could be this. And you measure the probability of obtaining the outcome. And you get a matrix. So you know the probability that you measured. You know you don't know this ideal, but you know the matrix. Like if I prepare 0, that would be the preparation. Uh, 1 might be the probability of getting 1, and you might also probability of getting 0. So you get a matrix. Let's say 1 qubit, you get 2 by 2 matrix. So this would be, for example, 0, 2, 0, 0, 1, 2, 0. So you get a 4 by 4 matrix M. So then you want to find the ideal measurement outcome. What you do is take the experimental measures matrix probability vectors, and you do the inversion. So really just inverse times the measurement, give you the ideal. Okay. So this is management mitigation. Okay, so I won't talk about read out so state preparation characterization in too much detail. So, but instead I'm going to switch to notebook that I uploaded. It's from the documentation. So I'm going to share. If you can go to the Brightspace and then download the notebook. I'm trying to find my. Okay, this one is from documentation. Yeah, it's downloaded from here. You can go to the link. This I supply the link here. This is from the IBM's documentation on error mitigation and suppression. Right. So I what I was talking about was mitigations. Uh, there's also suppression. It's called dynamical decoupling. We have seen from some of the notebook they apply XX, XY, XY, these kind of gates. The idea is try to cancel out some of the noise. So this suppression technique, this kind of suppression dynamical decoupling was used in the nuclear magnetic resonance quite a lot. That's yeah. So this is the package or the notebook from the documentation. So they talk about some package that requirement. Okay. Let me see if I can run this. Okay, so I'm still importing some required packages using V2 and runtime. I'm trying to find the least easy one. I think for this code, you can run on the device. Let me just print out what is the least easy backend. This is the Brisbane. Brisbane. I think this is here. You can actually go to the web and see Brisbane. It will show you how many. Okay, there are two jobs, so you can actually run this and then you'll be able to run it very quickly. Okay, let's go back. The first is the dynamical decoupling, which I just said. So maybe you can just read through the description here. So it's a sequence of microwave pulses, but that usually would mimic the X, Y, or Z. Actually, only X and Y. Z was sort of reference frame, and you can tune it by the different timing. Okay, but basically they use a sequence of microwave pulses need to be scheduled and run at precise time interval. It says unwanted interaction with the qubit can lead to coherent errors and idling qubit. So this is designed so that if you are running a circuit and there are wires that do not have any gate, that means the qubit is idling. So it's when it's idling, it will be susceptible to this T1 and T2 relaxation and decoherence. Yeah, so the idea would be to apply the idling qubit some pulses that actually can cancel the effect of some of these error. Not all, but approximately. So it says each inserted pulse sequence amounts to an identity operation. So eventually, in terms of gate, these should cancel out to identity. But the physical presence of the pulse has the effect of suppressing error. Yeah, so as we see before, there are many possible choices of pulse sequence. Well, previously we saw was not in terms of pulse sequence, but in terms of these XY labels. And which sequence is better for each particular case remain an active area of research. They might have a paper link for that. Yeah, so this paper the paper that is link point to may have further discussion. Yeah, so this is only useful when you have a gap. If you compress the circuit so that each instance you have gate applying that, then you 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 don't have the advantage of using dynamical circuit. Okay, if operation, yeah, as I said here. This shows an example of the XX whole sequence. Okay, this is abstract. Circular left is mapped to the microwave whole schedule on top. So you have Q0, you have an X gate, and you have these ECR gate, echo resonance, echo, what is cross resonance? Yeah, echo cross resonance gate. Yeah, here. And then another echo cross resonance gate, ECR gate. This is represent their timing they apply. So, but you see that this part is idle. Actually, this part is also idle too. So, but in this example, they apply the x times x supposed to be identity, so they apply to these this idle qubit with a sequence of two x pulses. You could also apply a negative x pulses because there may be this something difference that can actually balance cancel out the noise. Yeah, so dynamical decoupling, this is why I call dynamical decoupling. You want to decouple the environment that act on the qubit. It can be enabled by setting enable to true in the options. Sequence type, we saw a few sequence. I think in our previous one, we already see that. So the default is exact. The following cells shows how to enable dynamical decoupling for estimator and choose dynamical decoupling. Yeah, I think we copy this also in other notebook. XX use tau plus x tau is let's see what tau is the idling between the two. Tau is this time. This tau over 2 plus x tau plus x and then tau over 2. So that will be the sequence. So you also see that it could also be minus x, so it's x plus and x minus. You could also have 4 x using y in this combination plus x plus y minus x minus y. Let's go x, y, 4. And we use this sequence earlier. So for example, you could set this in the option here, estimator equal to estimator mode equal to backend, and then the options estimator options dot dynamical decoupling enable true, and then you can choose the sequence time. So the next one they introduced is called polytooling. is called randomized compiling. I already introduced one, which is the randomly adding the z at the end. This is just to improve the readout, actually to get rid of the y and x noise, and then you can just concentrate on the z part, which corresponding to the flip error. But this is more general, apply to the bulk of the gate sequence. So this is a technique used to convert arbitrary noise channel to poly channels, more specific structures. Okay, so this poly twirling is a special kind of twirling that uses poly operation. This fact to transform any one channel to a poly channel. Yeah, can mitigate coherent noise. Yeah, because it says coherent noise tend to accumulate projectly the number of operations. Poly noise accumulate linear. Yeah. Coherent error usually mean like unitary gate. For example, you can rotate, you want to rotate some angle, but you may over rotate. Yeah, so it says body twirling is combined with other error mitigation technique work better with body noise and with an arbitrary noise. You can see the example here. Lambda, you mean lambda? Oh yeah, sorry. Lambda is some channel, could be referring some kind of channel or operation. Right. Okay, so this is like sandwiching a choice of set of gate. Could be, for example, set of U with randomly chosen single qubit. So P is any faulty could be X, Y, or Z. The way that the ideal effect of the gate remain the same. So for example, if you have a U and P, you could transform this to lambda P. It may not be the same. For example, you could apply the X. For example, we know the control NOT gate. If you apply, let's see if I can write. Let me go to the slide. Yeah, so for example, you have some rotations, Ry, angle. If you apply, for example, X and X, this will become a negative angle. So we'll change that. For example, X ultimate gate. If they commute, if X move to the right, be a Z gate. If I can apply Z, then this will be identical to this. But here there's a negative angle, so it's not the same. But I don't know, I may apply, instead of this, I may apply the negative angle and I do the X to move it back to Ry. So you could do that. But so do we want to keep the original gate? It depends, yeah, so it depends. It depends how you want to design your, usually they want to maintain the same. So for example, if you have a C naught, if I have an X, I move through that, it'll become an XX. So maybe when you are having a CNAP, what you want to do the twirling is apply. Okay, this is what I mean is this is so if you do this, this will be the CNAP. So if you want to maintain, you need to use the circuit, the gate commutation and see that. But this here is setting up some general framework. We also, for example, this is general, and this is if they are the same, you have P and P prime sandwiching U, same that this imply, of course, imply this identity. So this lambda may represent some kind of error channel. So you have U tilde, which is an error gate. You can model it as maybe a channel followed by ideal gate. And this will be, for example, the error here. Using these identity, it can just become another error channel, lambda p, followed by the ideal gate. And this lambda p can be totally true. So in some sense, you want to average out the error channel by the poly. So in a cell become a poly channel if it were not in the beginning. So we'll just convert it to a poly channel, which is easy to deal with. Okay, they already said that here. Let's see if I miss any description. The result is that a single circuit is replaced with a random ensemble of circuits, all with the same ideal effect. When sampling the circuits, samples are drawn from multiple random instances rather than a single one. So you see that you have many different instances of P randomly, like X, it could be X, Y, etc., or Y, X, etc. You need to have, or sometimes you don't have anything identity, so you want to average of them. So you run many instances of the circuit, you combine the result, your measuring outcome will be combined. Since most of the error in current quantum hardware come from 2 qubits, so as you see, the 1 qubit has lower error rate, 2 qubit has a higher one. So this technique open apply exclusively to the 2 qubit gate. Yeah, for example, these are the circuit identity. Z, 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 but doesn't affect, and X would get pulled through with 2X. You could also have Y. This echo cross resonance gate has this symmetry. So if you have X, X, Y, Y, X, X, Z, Z, and X, X at the qubit one, their identity. Uh, okay. Yeah, so you can also enable this to be true and totally. There's also two other options, number of circuit instances. So you can say how many number I want to do P. Of course, the more expensive, and number of shots. Sometimes you want to average of these random sample. You don't need to repeat many times. Shots, meaning the shots. It's identical circuit, but repeat many times. Maybe you just repeat small amount of times and you have maybe combined with different or more randomized example. So you can do that by specifying the choice here. So here, the estimator options, twirling. So you have twirling here. And previously we talked about dynamical decoupling. So you just say twirling. And what is options? You want enable that true, and you want how many randomized gates and how many shots per circuit. So I talk about using the random Z to make it classical, but there's also a different way. That's mostly a thing invented by IBM. It's called twirled readout error extension. This is from this paper. This is IBM people. Right, measurement. This is mostly for the readout. So they consider a simple method force the bias in the expectation value to appear as multiplicative factor can be measured directly and removed at the cost of increasing in sample complexity. This was already previously discussed. Product single qubit general noise model. Okay. Yeah. If you want, you can also read the paper in detail. So what it does is actually apply Qiskit, which are accomplished by randomly succeeding emission. So it's randomly somehow doing the not gate. And if you apply it, you measure, you know you have a gate X, right? You flip the classical outcome, you can just classically flip back. So they say that this twirling has the effect of diagnosing the readout. Error transformation make it easy to invert. So this matrix 2x2 matrix or even larger set can become a lot hard to implement the inverse. So if you can diagonalizing it to make it diagonal, it would be easier to do the classical part, post-processing. So we don't discuss the detail, but they can be implemented easily. You say here, measurement mitigation, let's say to true in Qiskit resilience option. So this is incorporated in the resilience options here. Resilience, measurement, mitigation, true, and measure noise, noise learning, how many random, and shots per randomization. This one that is what I just talked about on my slide. It's the called zero noise extrapolation. I think I might lose my voice quite quickly. So this is what I just said with the diagram that I show. Suppose you have some noise strength and you can amplify, you can stretch that, just like stretching the gate. Then you can do that a few points and extrapolate. Okay. But for us, the users which are not directly controlling the pulse, it would be easier just to do the mitigation by the gate as a whole. So you apply the gate and apply the inverse. So this is you apply U and apply U inverse, and apply U, etc. Ideally, this should be the same. U dagger should cancel out, and you can just extrapolate. You can do that by setting the mitigation to true, so they call zero noise extrapolation. The following options. noise factor extrapolator. So yeah, so there's important issue here is we have a viewpoint. How do we extrapolate to zero? It depends on how you extrapolate. It will affect your result. So you also have some choice here. Usually we do the exponential extrapolation because the larger the noise, the sort of exponentially kill the coherence. You could also do the linear if these are small numbers, small like all the one factors, then you could just do extrapolation. Yeah, so this is how you enable that. This is also in the resilience options there. Okay. Usually I can show you, we actually did that, implement that in one of our work. Let me just simulate. Simulating. Okay. Keyword simulating. So this is the one that we did. So I can show you the real data that we have. So I have more figure. Yeah, so this is one example of the data. It's real data. So zero noise extrapolations. So this will be without extrapolation. And I do a U inverse. So I do U inverse, U inverse, and U. So I do one more. How many times you count the U inverse together? So that I have one here, I have 3, 5, and I extrapolate to 0. That would be the ideal case. In this case, you see that it seems exponential extrapolation is the better option because you see the data, it does not fit linear. So we do this extrapolation. Why the more you do this universe, it goes 1 or 0. 0. Because we are measuring some expectation value. Oh. And these are poly. Usually would depolarize to the identity. There's a negative down there, 0. Yeah, this is energy, so energy, so negative. Yeah. So that's one example. In particular, for this particular work, the extrapolated results actually are off, but we sort of have a reference state that we call it bell pairs. And by measuring the energy of bell pair and doing the same extrapolation, their ratio will give you how much off. Their ratio should be this, should behave similar. But if you know the exact bell pair energy, then you can do a correction. It's like I would like to compare this to like you need to have some unit, like in the calibrate. In cosmology, you use type 2 supernovae as some kind of distance reference, something like that. Okay, so this is the actual effect. Yeah, so maybe just in this, we ran on this IBM device. This was it's not Washington. I think it's Washington, IBM Washington, but it's retired a long time. We could get 102 qubit at most. Just to show you the results. Oh, For example, we were targeting the XXZ model energy, and these are collected results from different machines over different machine, different number of qubit. Of course, you see the error bar is not small, but this is really just a scale of from the range of energy, which looks large. But if you extrapolate, you get an energy per site, which is close to beta ansatz, about 4%. This is done like long time ago, 2022. So I believe the machine is much improved, so the result can also be improved dramatically or substantially, if not dramatically. Yeah. Another one is called probabilistic error amplification. Also, this is also developed by IBM Group. Yeah, so it says the challenges of zero noise error extrapolation, which I already show you one demonstration. Accurately amplify the noise affecting the target circuit. The one we use is called gate folding. Yeah, it's an easier way to do that than the pulse, because pulse is hard to control. Have to also have the access. Yeah, but there's also issue of ZNE potentially may lead to incorrect result. Also depending on how you extrapolate. Yeah, so there is some discussion here. This favors scalable error mitigation for noisy on circuit, but this is competitive expectation. So they developed a probabilistic error amplification technique. So they call this PEA, is a more sophisticated technique from perform preliminary experiment to reconstruct the noise, and then use this information to perform an accurate amplification. So then you need to learn the noise. So you start by learning the total noise model, each layer of the tangling gate in the circuit before they run. After the learning phase, the circuit are executed at each noise factor, where every entangling layer of circuits is amplified by probabilistically injecting a single qubit noise. So you would sort of inject single qubit there as a noise, proportional to the corresponding learned noise model. Yeah. So there's also this paper, the utility paper. This is a famous paper by IBM that they do some kind of noise mitigation. I don't think they do the full scale PEA. Maybe just to see the diagram. I think they also have this kind of extrapolation. Yeah, right. You see the noise model, this, and yeah, so you will see some of these extrapolation, noise, gain, and you extrapolate to zero. Depending how you extrapolate, you might get different results. If the result is more or less independent of how you extrapolate, then you can trust the result. So mostly today we discussed the description, but next time we can show the code in more detail. Yeah, so PEA, probabilistic error amplification, you would have learning. You learn the toward noise model. So you apply the trolling that we talk about, and then you learn that troll model. Noise amplification, you strictly troll gate randomly. Yeah, at different noise factor. The more random gate you throw in, the more error you have. Then you know the strength and you can extrapolation. The idea result estimate by extrapolating noise expected failure with respect to zeros. So this is still a kind of zero noise extrapolation method. It's more sophisticated. For utility scales, PEA is often the best choice, but it's also very costly because PEA is they already said that. I already said that ZNE noise amplification technique. You also need to enable, okay, in the programming, you need to enable ZNE to be true, and then resilience ZNE can be used to do the extrapolations, amplification level. Okay, PEA require noise model because you try to learn the noise, and so you need to have some model. Okay, so this is how you would enable that right here. ZNE amplifier. There's also probabilistic error correction, cancellations. Uh, maybe this is okay. So there is no actual example running the code, only the option. So I'll try to find one. I think there was an experiment, and also yeah, this corresponding to this paper, there is a notebook. You could also do it on similar. You could call the fake backend, right? Let's just finish this one. This is also proposed in IBM's group. It's called probabilistic error cancellation. Yeah, so unlike ZNE, it returns an unbiased estimate of expected value. However, it generally incurs a greater overhead. So in probabilistic error cancellation, effect ideal target circuits express a linear combination of noisy circuits that are this. So these are the observable ideal, and then this noisy one. The output of ideal circuit can be reproduced by executing different noisy circuit instances drawn from a random ensemble defined by linear coding. So this is saying that we say noisy circuit is sort of combination of ideal with some other different ideal gate. You can actually simulate, but you could go the other way around. Ideal circuit is a summation of different noisy one, like this schematic represented by this equation. So then you can invert that. Yeah. So the output ideal circuit can be reproduced by executing different noisy circuit instances. That's what I said. And drawn from a random ensemble defined by the linear combination. If the coefficient eta form a probability distribution, they can be used directly as probability of the ensemble. In practice, some of the coefficients are negative. Yeah, so they form a quasi-probability distribution. This can be used to define a random ensemble, but there is a sampling overhead characterized by these some of the nodes. The sampling overhead has a multiplicative factors on the number of shots. Yeah, if this gamma is large, then you will need to increase the number of shots to make the statistical error small. Yeah. In turn, scale exponentially with the depth of circuit. So you can enable this also in the resilience level, DC mitigation. Okay. So maybe here, this tutorial is the next time. So we won't have a class Wednesday. It will be the replay by this conference that we have in the Hilton Garden Inn. If you register, you can have breakfast there, and there will be also lunchbox. So the idea of participating is that you will see from the educator's side about quantum information. Yeah. Okay. So maybe we could look at this notebook if it can be wrong. Yeah. I think I think I might have already have this and also run this. Yeah, I think I have. I do have that collected in my collections. Yeah. Okay, maybe that's it for today. So no class, no lecture Tuesday.